Hey scientists, we're working on the flood module in Concord Consortium. We're working on the second lesson called Here Comes the Flood. And we're going to let it rain. Have you ever seen the Weather Channel as it forecasts weather across the United States? The radar shows large bands of rainstorms moving from the west to the east. The storms vary in length, how long they will last, and their intensity, how much rain they will drop. Both the duration of the storm and the amount of rain that falls influence the risk of flooding. Risk is the likelihood of people and their property being impacted by floods. Use the Flood Explorer below. You'll investigate how precipitation affects the size of floods. Remember, precipitation is part of the flood diamond. And we'll go back to the flood diamond later in this lesson. To do this investigation, run the model with several different types of rainstorms. You can adjust both the storm duration and the amount of rain. The size of flooding is measured in the total flooded area shown in the graph. Be sure to keep track of the investigations you run. So, this is the amount of rain here. Let's set everything to medium for the first one and just run that and see how many acres we can flood here. It'll be sunny for the first couple days. You won't see any rain. And then, well, I don't know that we're going to get any flooding if everything's a medium. We'll let that keep running. And I'm just going to put AOR for amount of rain, and that's medium. And this is how I'm going to keep track of what I did. My storm duration was medium, and my starting water level, that's SWL, starting water level, how much rain or how much water was already in the river was medium. You can think about starting water level as like a glass of water. The starting water level in this glass of water is pretty low. I'm going to need to pour a lot of water from a pitcher to get this to overflow. And just like a river, if the starting water level is low, it's going to take a lot of water to make that river flood. Let's move the starting water level up to high. Let's reload this. Oops. Let's reload the simulation because we didn't get any flooding. Let's move the starting water level to high. And let's see if that gets us some flooding. Ooh, we're getting a little bit of flooding there. So we can record this. That looks like about 800 acres. This flood area is measured in acres. That would be hectares if it was the last one was 0 acres flooded because we really didn't ever see the graph. This time, everything is the same except the starting water level was high. And we flooded 800 acres. Let's get the starting water level high here. And let's pump the storm duration up to, let's see, what can we do here? Let's reload. Let's go very long. So storm duration, very long. We'll keep the starting water level high and we'll keep the amount of rain medium. We'll see how this all works. Are we going to see any flooding here? The starting water level is now high. So if the river is like a glass of water, it looks like this. You don't need to add much to this glass of water to get it to overflow. There's already a lot of water in this river. And that's why we see when the water level is high, we see more acres flooded. We also see the duration of the storm is long in this case, which also leads to more flooding. So we had the amount of rain medium, but we had the storm duration really long. So it's raining kind of a medium amount, but it might be raining for a couple of days. The starting water level is already high, meaning there's already a lot of water in the river, so it doesn't take much to get it to flood. And we can see that makes a big difference because this time we flooded about, if you look at the second number, it's a coordinate pair. X is the number of days and Y is the number of acres. So we flooded about 1,600 acres. So let's reload. This time I'm gonna max everything out. So storm duration is very long, amount of rain is heavy, starting water level is high, and let's just try to see how much flooding we can get here. As we watch the map, you can see the river flood its banks. You can kind of see that the land being covered with water. And you can stop it right here if you kind of want to take a look at what's flooded. You can see Silverton, the town, isn't too flooded here, but some of these more rural areas where there isn't anything built up are they're pretty covered with water. But that's okay because there's nothing there that isn't going to that's going to be damaged by the flood. And we'll let that go down. Stop it. We'll get the number of, remember you want to take the second number at the top here, so that's 2141, so that rounds to 2100. So with everything maxed out, we did 2100 acres. And we had our amount of rain high here. So do other combinations, so run the model selecting very heavy rain in a long duration storm. What's the maximum number of acres during the flood? We can flood heavy rain and a long duration. Let's see where we did that. Heavy rain and a long duration was about 2100, but if we did, we didn't do that combination. Let's go back and do it quickly. Heavy rain, long duration, let's go. How high is it going to get? About 1400. So we already did number 2, experiment with different durations for heavy rain. In which scenario does heavy rain not lead to flooding? Well, when you've only got, when starting water level is really low here, you can put a lot of rain into that river before it floods. So starting water level low is a low risk for flooding. Do other combinations of amount of rain and storm duration cause flooding? Well, let's just kind of reason this through from our real life experience. If it's just kind of a very light rain and it rains for a whole week, nothing around here in Minnesota floods. Medium amount of rain with a long duration, if it's a good solid rain and it lasts a week, yeah, you can be in trouble. It depends. For heavy rain with a short duration, it depends on what you mean by heavy and what you mean by short. There have been some storms that have dropped 15 inches of rain in a day. And so that can be a storm event too, because the ground can't absorb all that rain very quickly. So either one of these would really be a scenario that could cause a flood. It also, of course, depends on how much water is already in the river. From the investigations you conducted with the model, how does the amount of rain and storm duration affect the likelihood that people in Silverton will experience flooding? Well, if you get a lot of rain for a long time, you're going to be flooded. Lots of rain for a long duration equals a high risk of flooding. Now, this is not the answer, but it's a good word bank to start your 1 or 2 sentence answer for that question. All right, back to the flood diamond. Here, remember the flood diamond is precipitation, what's coming out of the sky, topography, the shape of the land. Is it hilly? Is it flat? Permeability, how much rain is going to soak in. And the water table, how much rain, how much water is already in the river. In 1991, 1999, 2004, 2008, and 2016, the town of Elkader, Iowa, along the Turkey River, experienced 500-year floods. That's 5 500-year floods in only 25 years. Below are some pictures of the town during the flood. Let's go take a look at those so we can kind of get a sense. That's a big flood. The Turkey River just kind of spread way out because this is a pretty flat area here. And we can see if once the river rises above its banks, it just can go a long ways there. What is a 500-year flood? Well, that means a 500-year flood corresponds to a certain height or level of the river. Based on historical flood data, they can go back and from geology, tell where floods have occurred, where very large floods have occurred, and how often those have occurred. A 500-year flood level would be expected once every 500 years. Below are simulation results for Elkader, Iowa, with simulated 10 and 500-year floods. So this is a 10-year flood. You could expect that to see even in your lifetime. Once every 10 years, about the river will look like this. Once every 500 years, the river will look like this. This whole basin fills in. There's a lot more flooding acreage on the right here in the 500-year flood. What causes floods to be different sizes? Well, you can see how topography affects where water flows. In this activity, you'll explore precipitation and water table in the flood diamond. So the top and the bottom of the flood diamond, and how these two factors influence the size of flooding measured in acres. So the size is called extent. Which flood covers a greater area? The 10-year flood or the 500-year flood? So you can figure that out by looking at the amount of blue. Which one has more blue? Where does the water cover more acres or more land? Which flood is more likely to occur? Well, once every 10 years seems more likely to me. Now, look at the real photos of Elkader, Iowa along the Turkey River when it flooded in 2016. The flood shown in the photos was a 500-year flood. This was the 5th time the Turkey River flooded to the 500-year level in the past 30 years. What do you think caused the Turkey River to flood to a 500-year level so many times? Well, you can think about some of the stuff that we went over at the end of lesson 1. We can see that the trends in flooding in the Midwest have been changing. These green triangles mean floods have been going up. The brown triangles mean floods have been going down in the Southwest. And that trend of the floods going up, probably, since we're focusing on these two parts of the flood diamond, probably has something to do with precipitation, how much water is coming out of the sky, that might be increasing, or the water table, which is how much water is already in the river. So see if you can make a prediction that has to do with precipitation and water table. How much water is already in the river? So rainy days ahead. In activity 1, you looked at the topography factor in the flood diamond and learned how low-lying areas near rivers called floodplains are likely to flood first. But the flood diamond includes 3 other factors. Now let's investigate the precipitation factor, the amount of snow and rainfall. The amount of precipitation that an area gets every year can vary. For example, some years are drier than others. When many, many years are dry in a row, that trend can be considered a drought. On the other hand, over the past several years, some areas of the United States have experienced an increase in precipitation events greater than the national average. Here in the Midwest, we're getting more precipitation. Anything that's green is a percentage of precipitation change here. The lighter greens are less positive change. The dark green, it means it's 15% or more of rain extra every year. The Southwest is going brown, which means it's a negative trend. It's 5 or 10 or 15 or 20% less rainfall over a year. So the Southwest is experiencing a drought, and the Midwest is experiencing a very wet period. So we've looked at the map on top. Which region has experienced increases in precipitation compared to the 1901-1960 average that they used as 0, the middle? So which region is getting darker green? Which region has experienced decreases in large flooding events? So which region is getting darker brown? Based on the 2 maps, what is the relationship between the precipitation change and the flood magnitude in the Midwest and the Southwest? Well, let's look carefully at both maps. There's more rain in the Midwest, and there's less rain in the Southwest. And we know that because it's green, which stands for 5, 10, or 15% increase in rainfall per year, compared to the 1901 to 1960 average, which would be 0. If you're getting the same rain, you're here at 0. If you're getting less rain, 5% less or 10% less or 15% less or even 20% less, you're colored brown on this map, and that's the Southwest. Let's look at who's flooding and who's not. The Midwest has a lot of increases in flooding. There are some brown dots in some places, but mostly, especially in Minnesota, there are a lot of green triangles here, indicating there's an increase in flooding. Now we're getting more rain and we're getting more flooding. That makes sense. The more water you put in something, the closer it is to flooding. The Southwest is on the other end of things. There's less rain, there's less water around, and there's less chance that it's going to flood. And we see that on this particular map as the brown triangles here in the Southwest region. So if we want to type a relationship, we need to say something like more rain equals more flooding. We see green that indicates more flooding and more precipitation on both maps in the Midwest. And you can write a sentence that starts with less rain equals less flooding. What information on the map do we see that supports the idea that the Southwest is going to see less flooding? How certain are you about the relationship you described about precipitation change and the flood magnitude in the Midwest and the Southwest? Well, correlation, just because the data is trending in the same direction, does not mean it's causation. But in this case, since water tends to travel to a river, if it rains, we can be pretty certain that more precipitation is causing more flooding. Just because we understand that topography drains all of the water that flows on hills and mountains and forest, anything that's sloping towards the river, if it rains there and it doesn't get absorbed, it runs into the river. So we understand how watersheds work. Watersheds is an area that runs into a particular body of water. And we understand how rain works. We understand how flooding works. Too much rain in too little time, and you get flooding. So you can come up with answers for number 12 and number 13. All right, let's think about how communities keep us safe. Monitoring rivers hundreds of years ago, floods were harder to predict. Now scientists can monitor the water level in rivers to forecast when flooding is likely. Scientists use a variety of instruments to monitor the water level and flow of rivers. Watch the video below about the city of Raleigh, North Carolina to learn more about how they use instruments to help lower the risk of flooding in the communities near rivers. Now, Minnesota uses these same kind of instruments in our rivers, especially the Mississippi that we live quite close to.
Hi, it's Julia with the City of Raleigh. If you're familiar with our area's streams and creeks, you've likely come across one of these gauges. City crews, along with crews from the U.S. Geological Survey, are installing more of these monitors to add to a network that's already in place. And there's a good reason for it.
These gauges are about keeping residents safe, and that is our #1 priority. The gauges monitor stream flow and rainfall. This is particularly important because it allows us to know ahead of time any possible flooding impacts that residents may see in this area. The data is then used to determine road closures and evacuations leading up to and during a storm. The data also helps staff monitor and know when to lower city-owned lakes like Lake Johnson prior to a storm.
Data collected from these gauges is available online. You can go to the city's website and go to stormwater planning. The gauge information is towards the bottom of the page. Also, you can sign up for alerts from the U.S. Geological Survey to notify you about any potential flooding in your area.
Okay, so Raleigh's pretty smart about protecting its residents, and so is Minnesota. Many communities have these stream gauges. They basically tell you the starting water level. If you want to predict whether something is going to flood, it's very helpful to know if there's only a little water in the stream, and you can add a lot more before there's a flood, or if there's already a lot of water in a stream because it's been raining lately. And you can only add a little bit more before it floods. So, according to the video, how is the information from gauges used to help communities? Check all that apply. It determines road closures and evacuations, determines when to lower the water levels of nearby lakes. Basically, that would be a dam release. They lower the gates on the dam a little bit to let some water out. To predict flooding, to keep residents safe. You can put in your answers and check them. So let's look at this photograph. Data from this gauge is used to help calculate a river's discharge or stream flow. Discharge is the volume of water moving down a river per unit of time. Often in the United States, if you're a paddler, you know a lot about cubic feet per second or gallons per day. Many of the gauging stations that are online here in the Twin Cities, if you're people who like to paddle rivers, will check gauging stations to see how high the river is, to see if one, there's enough water in it to float your canoe or your kayak, and two, if there's too much water, it's dangerous to paddle. So they'll check gauging stations like this for safety and convenience as well. They're also good in storms. You can check if your neighborhood is likely to flood. And most of the data from these gauges is online. That's a little solar panel that helps that powers the gauge to send its data to a cell tower probably. If scientists observe high gauge readings, how might this information help the community? Well, we talked about if there's already a lot of water in the stream, then you only need a little bit more for it to flood. If there's only a little bit of water in the stream, then it can rain a lot before it floods. And that can help scientists figure out what the likelihood or probability that things will flood. High gauge readings help people know that only a little rain is required to cause a flood. And it helps them make decisions about, hey, do I need to think about evacuating? Looking at the weather and looking at the gauge, knowing that the river's already pretty high. You know, maybe I should make some phone calls and find a place to stay just in case I need to evacuate. And we're going to call it. We'll do parts 5, 6, and 7 of lesson 2 in the flood module in another video. Thanks so much for watching. I'll see you in the next video in part 2.